Hi everyone, I'm Amir Hossein from the University of Bristol. Today I will present Questar, our work on source-free video domain adaptation. The key idea is combining curriculum learning with collaborative self-learning to handle noisy pseudo labels when adapting video models to new domains without access to source data. You know that video models perform very well on the data they are trained on, but when deployed in a new environment, performance drops significantly. We call this domain shift. To address domain shift, we would adapt the model using target domain data. However, in many real-world scenarios, we cannot access the original source data due to privacy, legal, or storage constraints. This leads to the source-free adaptation setting, where we only have a pre-trained model and unlabeled target videos. Most source-free methods rely on pseudo-label-based self-learning, sometimes enhanced with vision language models such as CLIP. However, the core issue is that pseudo-labels are inherently unreliable. Some predictions are overconfident yet incorrect, others are uncertain but still influence the gradients. If we treat all pseudo-labels equally during training, errors accumulate and the model gradually drifts from the true target distribution. There are three main failure modes. First, overconfident noise. For example, a teacher model sometimes predicts with very high confidence but gets it wrong. The model then reinforces these mistakes. Second, uncertain noise. Even low confidence predictions still affect training gradients, causing instability, especially in the early stage. Third, there is no reliability control. Standard self-training treats every sample the same, whether the pseudo label is clearly correct or probably wrong. They all get equal weight. This means bad labels crop the learned features from the very beginning. The core insight of our work is simple. Not all pseudo labels deserve equal trust. So how do we fix this? We've proposed Questar, which has three key components. First, collaborative pseudo labels. Instead of relying on just the teacher model, we also use CLIP's zero-shot predictions. We combine them using a scheme called match or conf, which picks the agreed prediction when both models agree, or the more confident one when they disagree. Second, curriculum learning. We measure how reliable each pseudo label is by looking at whether the teacher and CLIP agree. High agreement means high reliability. We then train the model starting with reliable samples first and gradually incorporating harder ones using an exponential phase function. Third, adaptive curriculum regularization, or ACR. This detects when the model becomes overconfident on certain samples by tracking predictions history. If a sample has high confidence but subtle instability, ACR reduces its weights to prevent error reinforcement. Here is the full Questar framework. On the left is the collaborative self-training component. We use CLIP to generate zero-shot predictions alongside the teacher-student architecture. The teacher is updated using exponential moving average from the student to gradually incorporate target domain knowledge. Both CLIP and the teacher contribute to pseudo-label generation through a collaborative scheme. On the right is our curriculum learning module. We compute a reliability score based on the agreement between teacher and CLIP using bidirectional KL divergence. If the predictions align, the reliability is high. If they disagree, it is low. This reliability score passes through an exponential pace function producing a weight W. The weight controls the balance between two losses: cross-entropy loss, which learns from pseudo labels, KL divergence loss, which keeps the student close to the teacher. High reliability increases the influence of pseudo label, and low reliability shifts learning towards the teacher's distilled knowledge. Finally, the ACR module monitors the student's prediction history through a buffer. If it detects overconfident or unstable predictions, it will invert the weights to prevent the model from reinforcing errors. Let me briefly explain the reliability scoring and curriculum mechanism. We compute the symmetric KL divergence between the teacher and CLIP prediction distributions and transform it through an exponential function to obtain a reliability score between 0 and 1. If the two models agree, the divergence is small and the reliability approaches 1. If they disagree, the divergence increases and the reliability moves towards 0. Actually, here we don't apply a binary threshold. Every sample receives a continuous reliability value and contributes proportionally during training. We then combine this reliability score with an exponential pacing function, lambda of t, which increases over time. The final training weight is simply W equals lambda of t multiplied by R. Early in training, lambda of t is small, so learning is conservative. As training progresses, more challenging samples gradually contribute more. This final weight balances W times the cross entropy loss and 1 minus W times the KL divergence loss. High reliability increases trust in the pseudo label, while low reliability shifts learning towards teacher-guided distillation. Now let me introduce adaptive curriculum regularization, or ACR. Even with curriculum learning, the model can become overconfident on certain samples and reinforce its own mistakes. ACR works in 3 steps. First, we randomly select samples with a probability that increases over training, so ACR is mild early and stronger later. Second, we check prediction stability using a short history buffer. High confidence combined with unstable predictions signals overconfidence. Third, we partially invert the curriculum weights, shifting learning from cross-entropy towards KL regularization. On the right, you can see effects. Without ACR, confidence grows unchecked. With ACR, confidence is corrected when unstable overconfidence appears, leading to more stable training. This figure captures the core intuition behind Questar. On the left, without curriculum learning, every sample receives equal weight. It doesn't matter whether the pseudo label is correct or incorrect. They all influence training equally. Blue triangle represent true positive, and red triangle represent false positives, and they sit at the same weight level. In the middle, with curriculum learning, we introduce reliability-based weighting. Samples that are more reliable receive higher weights, while less reliable ones receive lower weights. However, curriculum learning alone is not enough. Some false positives may still appear highly confident and receive large weights. On the right, with both curriculum learning and ACR, we address this issue. ACR detects overconfident but unstable predictions and reduces their weights. You can see the cross-out point, a false positive that initially had high influence under CL but is corrected under CL plus ACR. Let's look at the results across 3 benchmarks. On daily DA, Questar improves over Dolby by about 1.4 points with ResNet 50 and achieves a substantial gain with the VIT backbone. On Expert DA, we consistently outperform prior methods with both backbones. On UCF-HMDB, we remain competitive with ResNet 50 and achieve the best performance with VIT. Here you can also see the closed gap metric, which shows the true adaptation effect. On Expert DA, we improve the gap closure by nearly 20% points compared to Dolby. This shows that Questar adapts more effectively towards the target domain upper bound. The ablation study shows how each component contributes, starting from the teacher-only baseline at 51.3%, adding clip for collaborative pseudo labeling gives the biggest single jump, adding curriculum learning brings another 0.9 points to 61.9%, finally adding ACR gives another 1.2 points to reach 33.1%. To wrap up, Questar shows that for source-free video domain adaptation, the key is not just generating better pseudo labels, but knowing how much to trust each one. Our 3 contributions work together. Collaborative pseudo labeling from teacher and clip gives us better labels and reliability scores. Curriculum learning uses those scores to prototype what the model learns and when. And ACR catches the cases where the model becomes overconfident, preventing error reinforcement in later training. The result is a state-of-the-art performance across 3 benchmarks, and we showed it works with both CNN and visual transformer backbones. Code is available on GitHub. Thank you.